Delhi University in the field of artificial intelligence and control. So presently, ma'am is working as a professor and head instrumentation and control department, NSUT, Dwarka, New Delhi, India. So ma'am having 6 years of industrial experience and 24 years of teaching experience in Delhi College of Engineering and NSUT, Delhi. So more than ma'am published more than 120 research papers in international journals and IEEE conferences. And ma'am guided more than 150 BTech and MTech students, and ma'am guided many PhD students also. And she is a director, technical business incubator of NSUT and NBA coordinator of NSUT. She is a member of NBA expert committee and the member of various committees of AICTE and UGC. She has organized IICPE 2010 at NSUT and in organizing committee of many IEEE international conferences in Delhi section. So besides teaching, she is actively associated with IEEE senior. She is IEEE senior member, ISTE life member, IETE fellow, and IE fellow. So once again, I am welcoming you, ma'am, on behalf of Electrical Engineering Department, Government Engineering College, Sonbhat, Uttar Pradesh.
Thank you, Dr. Chiranjeevi. I think you have taken my brief biodata from NSUT main campus website, and unfortunately
Yes,
it was not updated. I have now joined as a director East Campus Geeta Colony and of NSUT. So in IEEE, I am treasurer in IEEE in India Council, and the whatever you have read, it is 2 years back in my biodata. So there is a progress in that also. So thank you for reading my brief introduction, and I thank you for inviting me for this FDP of AKTU University, and I hope that many of the faculty members are from electrical engineering.
Yes, ma'am. Yes, ma'am.
All are from electrical engineering.
Yes, ma'am.
No, ma'am.
Yes,
I am from instrumentation.
Okay, so instrumentation and electrical engineering is one of the same thing. I am also professor in instrumentation and control engineering. So allow me to share my screen.
Yes, ma'am. You can share, ma'am.
My screen is visible to all.
Yes, ma'am. Visible, ma'am.
So as all are electrical and instrumentation engineering faculty, so my today's presentation is based upon my research work, and a few of my students have contributed to this presentation. So it is AI based motion control. Okay, so actually the image is not coming. Just give me 1 minute so that I can restart this so that images can come. Okay.
Okay, ma'am. Okay, ma'am.
So now images are coming. So I'm just again sharing. So good afternoon, everyone. Techniques include such names as fuzzy logic, artificial neural networks, genetic algorithms, and expert systems. AI is the family umbrella that loosely links these techniques and separates them from traditional computing methods. Each mimics some aspect of intelligence, human problem solving, learning, knowledge, or evolution. In this slide, some robotic arms are doing some operation on a car assembly, and in this area Two of my students have worked, and their papers are published in Robotica as well as in IEEE transactions. The first practical steps towards artificial intelligence were taken in 1940s. Today, AI is reaching a historical moment because of six converging factors. Bigger data. Many devices have given us access to vast amounts of data to process, both structured in database and spreadsheets, and unstructured such as text, audio, video, and images. As trillions of sensors are deployed in appliances, packages, clothing, autonomous vehicles, and elsewhere, big data will only get bigger. AI-assisted processing of this information allows us to use this data to discover historical patterns, predict more efficiently, make more effective recommendations, and more processing power. Accelerating technologies such as cloud computing and graphics processing units have made it cheaper and faster to handle large volumes of data with complex AI-empowered systems through parallel processing. In the future, deep learning chips, a key focus of research today, will push parallel computation further. So, as you might be experiencing while doing your research in your research areas, that with better computational power, better, bigger data can be handled, and if we, you can see that our globe is now more connected through internet. Whatever is happening in another country is instantly known to us through internet connections. So we can do the research which impact in real time very easily, and AI places a role in it. Global manufacturing supply chains together with social media platforms have fundamentally changed how individuals interact and what information they can expect and when. So it is the impact of connected globe. Open source software and data. If you are you have seen today's students working on Python, or many of them are using codes and on GitHubs. Actually, GitHub is the platform where the researchers share their codes on the GitHub so that other researchers can follow those codes and perform further in the research. So, open source software data are accelerating the democratization and use of AI, as can be seen in the popularity of open source machine learning standards and platforms. An open source approach can mean less time spent on routine coding. Actually, if you don't have such platforms, you will be just indulged in the basic research only. But if you are you have those availability of those codes which were made by researchers earlier, so you can work further. So it has saved much time for the researchers in the laboratories. Improved algorithms. Researchers have made advances in several aspects of AI, particularly in deep learning, which involves layers of neural networks designed in a fashion inspired by human brains' approach to processing information. Another emerging area of research is deep reinforcement, in which AI agent learns with little or no initial input data by trial and error optimization by a reward function. So research on AI algorithm has been moving quickly, especially since big data has combined with the statistical machine learning algorithms, and experts expect that supervised and unsupervised learning techniques will become increasingly blended, and that such hybrid techniques will open the way for human machine collaborative learning and for AI to develop more advanced human like capabilities. The convergence of these factors has helped AI move into in vitro, which is in research lab, to in vivo in everyday life. Established corporations and startups alike can now pioneer AI advances and applications. Indeed, many people are already using AI infused systems, whether they realize it or not, to navigate cities, shop online, find entertainment recommendations, filter out unwanted emails, or share a journey to work. So this is the base in which area of AI, or in how the AI plays an important role, and how you can which AI area you can explore. So there is intelligence in AI. Automated intelligence systems can take repeated labor-intensive tasks requiring intelligence and automatically complete them. Some examples may be seen in this area. And intelligence is of three types: assistance intelligence, augmented intelligence, and autonomous intelligence. So you may also explore which type of intelligence is there in the plant on which you are working, requirement of such things, and you can explore the literature survey and move forward in the uh, research area. So now I will give you insight of my research work. I have controlled a permanent magnet synchronous motor in vector control mode. Another name of this controller is also known as field oriented control. And this vector control or field oriented control is very popular in the area of AC machines, because in AC machines, controlling of speed and torque is not easy as it is easy in DC machines, because DC machines are only having two components of current. One is in quadrature axis, another is in the field axis, and these two currents, quadrature axis current and field axis current in DC motors, are 90-degree apart. So when we control only quadrature current, field current does not play any role, or it does not interfere in the control of quadrature armature current. And whichever, if we control field current, this armature current does not play any role or does not interfere in the control of field current. So these are independent currents, and control is very easy. If you have to increase the speed, you just control field current, and if you have to reduce the speed, you just control the armature voltage. So the controlling of DC motor for controlling speed is very easy. But if you think of controlling speed in AC motors, you need to control the frequency and uh, other things. If you have to reduce or increase the number of poles. So controlling the frequency or reducing or increasing the number of poles is not easy task. And currents in three phases are also interfering in each other's analysis. If you see, three-phase balance currents are 120-degree apart, and if you want to resolve these three-phase currents into one reference axis, then you will find that each one of them is contributing in the direction of that reference axis. So interference of other components of currents are very much there in AC motors. So controlling of AC motor is very tough, because you have to control the frequency and you have to see which vector is lying where. So how to control AC motors, and a technique was evolved that is known as vector control technique, in which magnitude as well as angle is controlled for AC motors. And what I can say in layman's language, that in this control technique, the AC motor is being run inside the computer, just like DC motor. So what we do, this is PMSM, permanent magnet synchronous motor, and this motor, why I have chosen this motor for my research work, because this is where it gives us very precise control. This has very low inertia, and this is very high torque to weight ratio. And so this application of this such a type of motors is where very precise control is required, like missiles, robots, and paper rolling mills, where very little jerk will also damage the application. So this load is that application where this PMSM is connected it is responsible to carry on that application. And as I told you that we require the information about its magnitude of speed and magnitude of angle at from its reference axis. That is taken with the help of resolver, and this resolver is taking information of magnitude and angle of the rotor position. It is taking the information rotor position and the speed magnitude. So rotor position is fed here and speed is fed in feedback path here. So this is actual speed and actual rotor position. So what we do, we want to run this motor at different speeds. So those different speeds can be given here as reference speed. So if we want to change the speed, we have to change this reference speed, and this reference speed will be compared with the actual speed, and an error will be generated here. This error will be fed to the speed controller, and the work of the speed controller is to reduce this error as fast as it can. And the speed controller may be PI controller, PID controller. These are classical approaches of the controller, and we can have the latest controllers also, like AI based controllers, like fuzzy logic, AI, and fuzzy logic, just having a fuzzy logic controller, or fuzzy logic tuned controller, or PSO tuned controller, or CSO tuned controller. So we can have any type of speed controller here. So the purpose of having different controllers and analysis is to find out how fast this change will happen, how fast our motor will be running at the speed which we want to run it at. So after this data of error is fed to the speed controller, output of a speed controller is armature component of the current, reference current of armature component. So you can see that there is a limitation provided after this block. This limiter is limiting this current value to the prescribed motor parameters. The motor has certain parameters. It has certain current parameter, torque parameter, and field current parameters, etc., and voltage parameters. So this limiter is keeping that in mind. So whatever output is coming from speed controller should be in within the limit, so that motor cannot be damaged. So we have to apply limiter here. So output is quadrature axis of armature current, quadrature axis current. So now here you can see two-phase to three-phase conversion. So why this is used? Because we have converted our three phases into two phase inside the computer, and we are applying this control just like a DC motor. IQ and ID only, now it inside the computer only two currents are there. We cannot see these three currents because we have already converted this IABC into two components, IQ and ID, inside the computer. And now we want to send the data into real time to be fed to the inverter gate circuit. So we have to convert this two phase to three phase, so that three phase current signal can go out from the computer. So reference signals are generated as a result of this block. So IA star, IB star, and IC star are three reference currents. For this block, angle position is also required in addition to these two currents. So with the help of these two currents and this angle, there are certain equations available in literature which convert two phase to three phase. So finally we have these three currents available here, which are the reference three phase currents. And here you can see small dots in the three lines. These three lines are the connecting electrical wires, and the sensors are connected into these three wires, and these sensors are taking actual current from here, and these are compared here by with the reference current. So actual currents are being compared with the reference currents, and finally difference between reference and actual is fed to the CCVSI in the form of pulses. So here you can see three wires going into CCVSI, but each one of them is generating two pulses for 6 IGBTs or 6 MOSFETs in this CCVSI. One in 3 in the positive directions, 3 in the negative directions. So one lead here is producing 2 pulse, one is positive, another is negative. Similarly, the second lead is also doing so that same thing, and third lead is also doing the same thing. So 6 pulses are fed to the current control voltage source inverter, and it is generating the current and voltage according to the required frequency, so that motor can run at the reference speed. So this is the explanation about this block, uh, and vector control of PMSM drive system is used here, which which converts any AC motor into equivalent DC motor inside the computer. And finally, signals are being sent outside by again converting DC motor parameters into its equivalent AC motor parameters, and we can use in real time. So this exercise was done using DSpace, and this DSpace is used to interface between hardware and software, and this is the same circuit, and the components are now shown here. CCVSI has 6 devices. It has got its gate also, and this is the DC bridge rectifier, which is input this inverter, and there are 6 pulses are coming, which I have already explained. And this triangular wave generator unit is very important here. We have to generate a pulse which has the frequency depending upon the switching frequency of these devices. If these are thyristors, then we have to generate these pulses up to only 10 kilohertz or less than 10 kilohertz. If these devices are IGBTs, then we have to generate this triangular wave generation unit at the frequency up to 20 kilohertz. And if these are MOSFETs, then this wave will be having up to 100 kilohertz frequency. So we have to select this triangle wave generation circuit. Okay. So this is PMSM, and rest of the thing is same. This is resolver, rotor position detector after this resolver, because we have the signal coming from resolver, that is electronic signal, and we have to get 2 electrical signals like angle, position, and another is speed. So we need a PCB here which calculates, which give us these 2 positions. So this is done using PCB, and this flux weakening block is required to increase the speed beyond its rated speed. So this is done mathematically inside the computer. To increase the speed of permanent magnet synchronous motor, as an electrical engineer, you might be knowing that permanent magnet synchronous motors are having their magnets buried inside the rotor, and these do not take magnetizing currents from the mains. These produce their magnetizing flux from within, from the rotor, where the permanent magnets are fixed. So we cannot change the flux of the rotor permanent magnets, but inside the computer we can introduce a component which is negative ID here, and with respect to how much change we want in the flux. So during calculations, the flux is reduced, and reduced flux gives us higher speed. So if we want to run motor at higher speed, we have to reduce the flux for any AC motor. And for PMSM, we are just introducing minus ID component inside the computer, but because it is not possible to control the flux of PMSM physically, because it is produced by the permanent magnets. So this is the electrical line diagram of the same circuit, and everything is now explained to you. So now starts our research. For that, we have to model our motor. Modeling of PM synchronous motor needs some assumptions. Saturation is neglected, through it can be done into account. It can be taken into account by parameter changes. The induced EMF is sinusoidal. Eddy currents and hysteresis losses are negligible. There are no field current dynamics. There is no cage on the rotor. So there are certain assumptions based on which we will model our synchronous permanent synchronous motor. So after modeling of the synchronous motor, modeling of conventional controllers is the second task. So modeling of PI controller, this is very classical approach, and these equations are well known. So using this well known equations and available MATLAB Simulink block set and power GUI set, we have created this PI speed controller, and here we need to tune the KP and KI for this controller. Second controller is PID speed controller, and the equations are well known, and we have to tune three gains KP, KI and KD here. Third one is sliding mode controller, and in sliding mode controller there are certain equations, and there is a pre-defined trajectory is there, and our model has to, our error has to be reduced by tracking that trajectory. So how fast this trajectory being tracked is is giving you the better output. So this is the mathematical modeling of the sliding mode controller, and here you can see C1 and C2 are controller gains on a speed locus, and K1, K2 are adjustable parameters. Modeling of artificial intelligence based controllers for PMSM drive. So this is fuzzy logic speed controller, and many of you have already worked on this controller. This requires human knowledge, and we should have prior knowledge about the system, and using our knowledge we have to write certain rules, and normalization of data is required before feeding into the fuzzy logic controller. That is known as fuzzification. After we will take error and change in error, and we will fuzzify our model using membership functions. And then rule base will be applied, and then defuzzification and denormalization is required. When fuzzy logic controller is designed, in Simulink, a Simulink block appears, and that block may be treated as black box. To that box, if you send the signal as input, that will give you better output than PI and PID controller, because now we have designed this controller based on the previous information about the system. So fuzzy logic controller works better than PI and PID for precise control techniques. And this is the Simulink model of fuzzy logic controller. And there is FIS editor in the MATLAB. Using that, you can model your fuzzy logic controller. The gains, tuning of these gains is very difficult. This is just decided by what input is coming, and you have to just normalize here it bringing this data from its actual value to value 1, and this is, you have to just tune it because it is derivative. The same signal is applied a derivative here, and then you have to select a gain here, and then this gain is also playing very important role. So these two gains are required to be tuned for getting better results. So designing the fuzzy logic controller is not tough, but tuning of this controller is tough. NFIS adaptive neural based fuzzy inference system controller. So this type of controller works better than all previous controllers which I have explained, because this has the quality of neural network as well as fuzzy logic. So it knows it is designed based on the rule base, and it has got the architecture just as neural network, and we have to train it also using backpropagation theorem. Certain work is going on my roof, so just bear with me. So here you can see the architecture of this NFIS controller, and we can write a rule, a code for this type of controller. And this is the MATLAB Simulink model of the NFIS controller. The next controller in AI is neural network controller, and it has got many input, and it can have many outputs depending upon what application we are working on. And the choice of hidden layer is based on the how much powerful full of your computer on which you are working is. Increasing the hidden layer will make it more complex, and in certain this laptops it cannot work, but if it is working and the laptop is of that configuration, it will give definitely better results. So this is the line diagram of neural network controller. You can see here the plant is my motor PMSM, and a controller is a speed controller. So it is a pre-defined speed controller which we have worked upon, that is PI or PID or SMC. So we know for this input what is output, and we record this input and output for those controllers, classical approach controllers. We will record it in MATLAB, whatever input we feed, and we will record output for that input, and this data will be used to train this neural network. So after training of this neural network, we get these two figures. This is regression graph, and this is error graph. You can see in regression graph, my three layers are completely coinciding. So if we get this type of regression graph, our controller will work better, and if error is minimized faster, then also the controller will work better. So here in 25 epochs only, the error is 10 to the power minus 5, which was defined by us, and all points are coinciding here. And here one thing is important to mention here: if we get this type of graph, this can be achieved after 5 and 6 attempts or more attempts, but once it is achieved, you have to save this graph, you have to save this model, otherwise again achieving this graph will be very difficult. So once you achieve this type of tuning for any AI controller, just save that Simulink model for that training, and don't lose this thing, otherwise you will be repenting later. So when you achieve this, in the code itself it is written that it generates the Simulink block for this particular neural network, which we designed for our speed controller. So this graph, this Simulink block will now be replacing our conventional controllers, and we are just take this from the MATLAB window and connect in place of our PI controller or PID controller. And the gain tuning is also playing very important role. And you can see rest of the things are the same for this motor, which was designed earlier in Simulink with PI controller. Then next controller is recurrent neural network. Here the architecture is different, and this learning algorithm may be same. So what is the difference in architecture can be seen here, that some feedback is there. In the previous neural network, their feedback was not there, it was feed forward path. So with this feedback, this become more intelligent, and it gives better result. So after training the recurrent neural network, this graph is generated, this Simulink block is generated, and we can replace the speed controller with this block now. So after modeling all the motor and all these controllers, we worked on this motor. The type of motor is interior type of PMSM, and rated speed is 780 radian per second. Motor rating is 2 HP, number of phases 3, number of poles 4, base current 8 ampere, rated voltage 240 volt, stator resistance per phase is 1.22, and you can see its inertia is very low, 0.001278 kilogram meter square. So this motor is there in my lab, available in my lab. So with that motor and those controllers, we have to take some results to analyze that whether these controllers are working perfect for our applications for which we want to run this motor. So certain applications require speed control, speed reversal, and lesser speed and very high speed. And if certain application require variation in load, so all those aspects are studied here. So here first figure is PI speed controller with starting and speed reversal with load perturbation. So starting can be seen here. Motor starts from its zero. It attains to its base speed, half of the base speed in 0.015 second. And then it takes, there is no change in the speed, and then the reversal is applied, and motor is reversed from 340 to minus 340. And you can see the smooth reversal is taking place because the tuning is perfect. And the torque is initially, every motor takes very high torque. So this high torque is how much high it should be. It is decided by that limiter, which I explained in my diagram. So I limited the torque here, otherwise it would be very high and that can damage the motor. So we have limited this torque, which is inherently very high for motors. It is 7 to 10 times in the motors, but we have reduced it to 2.5 times by applying that limiter, so that there will be no extra load on the inverter in the starting also. Then this motor has attained the speed whatever we have set. So the motor torque will come to no load condition, and uh, now the reversal is applied. So torque will also be reversed for helping this motor to reverse. So torque is reversed, so speed is also reversed, and then again torque is settled to its no load value. Now after certain time, we want to increase the load on the motor. So we have increased the load on the motor, and you can see there is slight variation in the speed. So controller is working very fine. And similarly, the torque is also proportional to current. So initially currents were high, so torque is high, so current will also be high. And no load torque, so no load currents. Then reversal in speed, reversal in torque. So you can see frequency of current is now reversed here. And then again no load current, then load is high, so current is also high. And here this is the position is one it is rotating in one direction, and here the direction is reversed, and then the direction you can see the change direction. So this is the explanation how we have analyzed motor for different type of controllers. So same diagram is for PID and same for SMC, but the difference is the starting speed time is 0.015, 0.015, but here it is 0.01. So sliding mode controller is found better in terms of achieving its speed, but it is very fast, but it is oscillating. So the fluctuations in the torque are there. So that can damage our application. If it is paper rolling mills, this jerk will certainly damage the papers. And if it is we are targeting a bomb or something is placed with the help of missile, so it can also hamper the operation. So PI speed controller with starting and speed reversal with load perturbation. You can see here the difference is we have increased the load, the speed from 340 to 1000. So the same thing is seen for PID and the sliding mode controller also. And you can see in the sliding mode controller there are fluctuations, but in PI and PID less fluctuations are seen, because we are not looking this speed at its close view. So later slides we will see the closer view, then we will find out which one is the better for very fine operation. So this is the speed reversal from very high speed, and you can see it is perfectly getting whatever desirable result are in the terms of angle, in the terms of speed, in the terms of torque and current. So this is the comparative study. I have already given you the comparison while explaining. So speed controllers in variable speed drive with load perturbation above base speed using flux weakening. So now we desire the speed to be more than base speed, more than its rated speed. So that require a flux weakening. So flux weakening, as I already explained, we have to introduce minus ID component, because we cannot reduce the flux of a permanent magnet synchronous motor. So by reducing internally inside the computer that flux, we can increase the speed up to more than 780 rpm. So you can see in each and every operation, more than 780 rpm motor is running successfully for PI as well as for fuzzy logic controller. But you can see here the fuzzy logic controller is always having some offset or steady state error. So this is NFIS controller, ANN speed controller and RNN controller, and you can see with the help of diagram itself, with the help of figures itself, that RNN is giving best results. 0.014, the speed may be attained at the same time, but if you will look at the closer view, this will give better result in terms of jerks, in torque, in fluctuations in speed. Speed controller in speed reversal and load perturbation with near load, full load torque. So again, the same thing is done. Near full load torque was given here. Here you can see how large the currents are now. It is successfully taken that motor can take full load also successfully with this type of controllers which were designed for the motor. So you can see full load operation. After reversing, we applied the full load. Speed controllers and speed reversal in flux weakening and load perturbation. So speed reversal we kiya and then full load we apply kiya, and you can see the results. So different variations were done to study the property of controllers. So finally, the result is RNN based controller works better than other controllers. Now, the next part of this talk is sensorless control of PMSM. So why sensorless control is required? Because we want to run this motor hassle-free, and this sensor in terms of resolver or encoder which you have seen is connected into the rotor, inside the rotor, but it is connected to the shaft of the rotor. So moment of inertia is also increased, and it also hampers the operation of motor, and it is costly also. So we researchers want to eliminate this sensor. For there are certain mathematical equations available which can give us the information about speed and its angle position with the calculation itself. So that can be replaced, sensor can be replaced. Advantage of sensorless control of a drive: a special mechanical arrangement is needed to mount the sensors on the shaft. The sensors are temperature sensitive, and the absolute position sensors are generally speed limited. Increase in robustness and reliability: resolvers need special external circuits to obtain the correct position. Cost and size reduction, maximum power density. So here, this is the similar line diagram which I explained you in the beginning. But here in the PMSM, if you see at the PMSM circle, that is the motor, we don't have any resolver connected to it. So without resolver, how we are getting the information about speed and angle? It is done with the information of current and voltages. Sensors are there, but main sensor, which is costly and hampering the motor operation, is now not required. And the sensors outside the motor are there, and these are not that much costly also. These are very cheap. So current sensors and voltage sensors are giving us information, and with the help of that information, we will calculate the position and speed inside the computer. And here in the current sensors requirement, you can see only two sensors are required because these are balanced currents, and if we know IB and IC current, we can calculate IA. So now three-phase voltage and three-phase current information is sent here, and this is calculating us for angle and for speed, and this is the reference speed. Rest of the things are same. So there are limitations of sensorless PMSM drive also. Suitable where weight and shape of the motor are of main concern. Low speed sensorless operation are quite critical since the motor back EMF is too low and rotor flux estimation results sensitive to stator resistance variations. MRAC, Kalman filter and other sensorless control schemes allow low and zero speed operations but often are too complex and extensive. Various schemes of sensorless speed control. So there are number of such sensorless speed drives are there. You can see the literature. I have worked on the last two, that are observer based position and speed estimators, and estimators using artificial intelligence. So there are two kind of sensorless vector control of AC drives. One is model based, another is non-model based. So model based technique require modeling of the motor or modeling of the controller. All the thing modeling is required. But AI technique do not require model based technique. These are called non-model based technique because they don't require model. They work on the data. So if we have data, we don't require any model. So I have worked on artificial intelligence based observer in non-model based technique, and observers MRAC Kalman filter in model based technique. So I have worked on both of them. These modeling of sensorless techniques for PMSM drive system. So this is the modeling of state observer available in the books, and you can find the equations available in the books. BK Bose has these equations, and this is the to estimate some of the state variables, say ID, IQ. The standard form of state observer equation is given by equation 21, and G matrix is having 6 gains, and tuning of these gains is required. So this is very complex method, uh, which is model based method, very complex. You can see these are 3 equations, and we have to realize these 3 equations into MATLAB, or we have to write code for this. So how much complex is this? You can see from coming slides. This is Simulink model of speed estimation, because we have to estimate speed as well as angle. So first we will find out the equation for speed estimation, that is 25, and we will just make its block. So similarly we will estimate IQ and ID, and we will make these blocks also, and finally we have to take outside as this speed and angle only. So you can see Simulink model of angle estimation block. So this is speed estimated, and rotating estimation angle, and these are the input, and gain, and then finally rotating angle is coming. And this I told you in the beginning, that this triangular wave is based upon the switching devices, how much switching frequency is required. We will fix the frequency here, and rest of the things are just comparison between actual current and reference currents, and 6 commands, 6 pulses are generated. So this is the total combined model of extended state observer based on extended Kalman filter. So you can see two outputs are coming: speed, estimated speed, and rotating angle estimated. And with the help of these inputs, we are getting these two outputs. So each one of subsystem is having a very complex connections inside these blocks. So this is very complex. But if we know for this output, this input, this output is coming, we can design our AI or neural network based controller observer very easily. But for designing that, we need data, and for data we have to design any classical approach observer. So I took this extended Kalman based state observer PMSM drive. First I designed this, then taking data from here, I designed AI based observer. So once these two observers were designed and their Simulink blocks were ready, I just connected this observer here in my model by connecting these, by giving those required input directly from the motor, and this observer was giving me the required output: estimated angle, estimated speed. So now you can see that this PMSM is not giving any information from its resolver because we have removed it. So only feedback is coming from the observer, and observer is inside the computer. So physically you don't require resolver. All things are being done calculation through calculation. The rest of the thing in the model are same. So again, similar type of observations are taken, and all such important observations which we have taken without observer, observer based control, sensorless control, are again taken, and you can see how beautifully the all angle, torque, speed, and currents are tracked for all type of variations. You can see for heavy loads also it is giving better results. And this is the starting of motor, how much time it takes, how smoothly it reaches its reference value with different type of speed controllers, and in observer type of motor without sensor. And this is the torque for the same time period. This is current for the same time period for different controllers, and this is angle for the same time period for different controllers. And this is the close view, how the speed approaches and it behaves when it approaches its reference value. So I told you that fuzzy logic is very smooth operation, but it gives steady state error, and sliding mode controller does not give that much steady state error, but it gives some fluctuations. So every controller has its drawbacks. Neural network has it gives smooth operation. It has lesser steady state error than fuzzy logic controller. So this is the reaching the speed up to double the rated speed is also possible through observer. Torque variations are normal in observer, from observer model also. Currents at higher loads are also traceable. Motor is running successfully, and reversal, speed reversal is also successfully being done here. Current are in, and the load is increased, so current is also following the increase in load. When speed is reversed, you can see the change in frequency here. Speed reversal is taking place. So you can see the close view when speed approaches its reference value. So these papers of mine were published, and based on these papers I was called by Air Marshal because he was also working on missiles, and he was seeking my help in designing fuzzy logic controller. So I went to his place to for further association with him, but unfortunately because of some accident in his residence, the things worsened, and we could not take it further. So this is the conclusion. Okay. Then third thing in my research is that resolver output is uh, fed to the PCB, and that making that PCB is very tough job. That PCB, we need some components, and component specific components, and after soldering those components, some component may not function, some component may malfunction. So this is very tedious job. I made around 25 PCBs for this, taking information from resolver. So it was very tough task. So one day I searched for one paper which was replacing this PCB with the help of software. So I started working on it. So RDC, hardware replaced by algorithm. This is the next work which I did. So this is that software which was replacing that lengthy complex PCB. So it just requires signal coming from resolver, and it is giving us angle position and speed position easily. So again, DSpace was used, and DSpace is the helping the same Simulink model to run my model for interfacing purpose also. So just slight modifications are required in my Simulink model, on which I have done simulation. I can use that same diagram, same MATLAB model for Simulink model for interfacing also. So these three signals are coming from my resolver, and this theta and speed is the output, and in place of PCB I am just using algorithm. So this is the diagram, actually interfacing diagram and Simulink model which was used to extract that information through DSpace in here, and these are enabled links of DSpace ADC channels, and through this the signal from resolver was sent to the DSpace, and DSpace is giving us the desired speed information, and angle is again after that angle was calculated mathematically. So this is the diagram in DSpace, Simulink model in DSpace, and these are the output. Actually, DSpace is having this facility that we don't need CRO. We just check all those signals into the our laptop screen also. So this is the signal coming from resolver, and it is muxed, and we have demuxed it and got the speed information. For different speeds, same operation was done, and it was working successfully. That algorithm was working successfully. Okay, and this is the fourth thing in AI based motion control. Nowadays many professors, every professor is working in renewable energy area. So some of them are working in PV and solar systems, some of them are working in wind energy converter systems. So many of my students have worked on so renewable energy systems, and many of them have worked in wind energy converter system. So this is the elementary work of one PhD student who has worked on wind energy converter system, and finally he published 5 SCI index papers in very reputed journals. So now this is the initial stage of his PhD. So this is the introduction of wind energy converter system, and this is a wind energy converter system block diagram, and this is the basic configuration of grid connected high power wind energy converter system. If you are working in this area, you may be knowing all these terms, and these are different type of wind energy conversion systems: DFIG based, SCIG based, and WRIG, SCIG, and finally he has worked on PMSG, permanent magnet synchronous generator. So PMSG is the generator which has the construction just like PMSM, but now it is used as generator. And here he has worked on tip speed ratio, and he designed two controllers, PI controller and fuzzy logic controller, for tip speed ratio of wind energy system. So if this switch is on, this one controller will be working. If this switch is on, this fuzzy logic controller will be working for his system. So objective is defined for this work, and mathematical modeling of wind energy conversion system. There are several equations available in different papers. These are just equations available for tip speed ratio. And finally, fuzzy logic controller was designed using MATLAB Simulink, and membership functions were designed. Rule base was written, and wind pattern was designed. And for this wind pattern, studied TSR, stator current, torque, and rotor speed. You can see wherever speed is changing, there are some perturbations in load current, and load power also. But for PI controller, these are high, and for fuzzy logic controller, these are reduced. So this is the comparison shown for the research work. So this is the conclusion. And for this work, finally, few references were used. Thank you. Any questions?
Thank you, ma'am. Any queries, participants?
Priyanka Singh and Archana, who are they? May I know? Actually, one of my student is named Priyanka Singh and another Archana. So are they same?
Ma'am, one ma'am is there, ma'am, Archana. Archana, ma'am.
And Priyanka Singh.
Priyanka Singh. Yes, ma'am. Priyanka Singh, ma'am, also there. Priyanka Singh, ma'am.
I think they are not listening to the talk.
They are not responding, ma'am.
Yeah.
Any queries, participants? I think no queries, ma'am. Everything is clear for them.
Okay. Thank you.
Thank you, ma'am. Thank you very much, ma'am. So in your busy schedule, you have accepted my invitation and given lecture. Thank you very much, ma'am. Thank you, ma'am. So thank you, participants. So tomorrow, first session will start at 10 o'clock. Thank you.